Hello everyone, I am Shivam Agarwal, a computer science student at IIT Bombay. I secured an All India rank of 27 in IIT JEE 09. I secured an All India rank of 56 in IIEEE 09, and I was a member of National Physics and National Chemistry Olympiad. So today I'll be delivering a lecture on three-dimensional geometry. We have already learned about vectors, we've already studied two-dimensional geometry. So today we'll be studying about three-dimensional geometry. So what's the basic or what's the striking feature of three-dimensional geometry? So here the most important feature which is different from two-dimensional geometry is that we have an additional coordinate. That is, in two-dimensional geometry we mostly deal with x-axis or say x coordinate, which is also known as abscissa, and y coordinate, which is known as ordinate. Here we'll be dealing with a third coordinate which will be along the z-axis. So I'll first start with the rectangular coordinate system in three-dimensional geometry. So the rectangular coordinate system. So it goes as follows, that in three-dimensional geometry we choose a specific point which is known as the origin, which is same as in two-dimensional geometry, and we have now three perpendicular axes, three orthogonal axes, the x-axis, the y-axis and the z-axis, and these axes when taken in order from x, y to z form a right-handed system, that is x cross y is positive z. So this is the three axes, this is our origin, the coordinates of origin are taken as 0, 0, 0, and any point P say has three coordinates, an x coordinate, a y coordinate and a z coordinate. So this is the rectangular coordinate system in three-dimensional geometry. Okay. So this is the basics of three-dimensional geometry. So now let's move on to some of the properties of three-dimensional geometry. Say we have 2 points. So first of all, I'll just jot down the properties. I'll go very order wise. Okay. These are some of the important properties. First is, say there is a point P, x1, y1 and z1. There is also a point Q, say x2, y2 and z2. So the distance between PQ is equal to x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square whole under root. So if we have 2 points P and Q with the coordinates x1, y1, z1 and x2, y2, z2 respectively, then the distance between both of the points is the square root of the sum of squares of the coordinates, of the difference of the coordinates. Okay. So the second formula is section formula. So it says that we have a point P whose coordinates are x1, y1, z1. We have a point Q whose coordinates are x2, y2 and z2, and say we have a point R whose coordinates are x, y, z, and R divides PQ in the ratio m:n. Then the coordinates of R are given as x equals to n x1 plus m x2 upon m plus n, y is similarly written as n y1 plus m y2 upon m plus n, and z is similarly written in the same way. So this is section formula. I'll once again repeat. Say we have 2 points P and Q with the coordinates x1, y1, z1 and x2, y2, z2. Then say a point R divides the line joining P and Q in the ratio m:n, m from the P side and from the Q side. Then the coordinates of the point R are given by this formula. Okay, so this is some very important formulas. Also, we have centroid of a triangle, centroid of our triangle ABC the triangle is here. This is point A with the coordinate x1, y1, z1. This is point B with the coordinates x2, y2 and z2. And this is C with the coordinates x3, y3, z3. So the centroid is given by, say, G. Centroid is given by, say, G, and say its coordinates are xg, yg and zg. And so xg is given as sum of the abscissas of all the points divided by 3. Similarly, yg is given as summation yi upon 3. Similarly, zg is given as summation zi divided by 3. So this is how the centroid of the triangle is defined. We have also the incenter of a triangle. The incenter of a triangle ABC is defined as that point which is the center of the circle which is inscribed in triangle ABC. So suppose the sides of the triangle are A, B, C in this notation, then the incenter of a triangle is given as I, say xi, yi, zi, then xi is equal to A x1 plus B x2 plus C x3 upon A plus B plus C similarly. That is, say the triangle is this with the length of the side opposite to the point A is A, similarly B and C, then the coordinates of the incenter of this triangle are defined in this way. Xi is equals to Ax1 plus Bx2 plus Cx3 divided by A plus B plus C. Okay, so here we learn about centroid and incenter. There is also one very important feature. We have already learned about tetrahedron in vectors. I'll once again repeat. Tetrahedron is a solid object, consists of 4 triangular faces. This is basically a tetrahedron with 4 triangles. So the centroid, say the coordinates of the triangles are x1, y1, z1, x2, y2, z2, x3, y3, z3 and x4, y4, z4. If the coordinates of the vertices of the tetrahedron are such, then the centroid of the tetrahedron is defined in this way, say G. So xg is summation xi by 4, that is x1 plus x2 plus x3 plus x4 by 4. Similarly, yg is summation yi by 4, zg is summation zi by 4. So here it is very important, or I would like to mention that what is the centroid of a tetrahedron. So the centroid of a tetrahedron is the point of intersection of 4 lines, and 4 lines are such that if we draw a line from the point A to the centroid of the triangle BCD, so these are the 4 lines, that is the intersection of the lines joining the vertices of a tetrahedron to the centroid of the opposite faces. So the point of intersection of those 4 lines is defined as the centroid of a tetrahedron, and the coordinates of the centroid of a tetrahedron are defined in this way, that is xg is summation xi by 4, yg is summation yi by 4 and zg is summation zi by 4. So this is the centroid of a tetrahedron. Okay, so these were some of the most important properties. Now let's move on to another topic. So this is about shifting of origin. So Usually we take our origin as 0, 0, 0. Suppose we want to shift our origin. Shifting of or translation of axis is defined in this way. Say initially our axes were such. This is say x, y, z. This was our origin earlier. So if we shift our axis such that the axes move parallel to them. This is y dash, this is x dash, and this is z dash. So the axes are still parallel to the earlier axis, only the origin is shifted, say to a point x dash, y dash, z dash. So say we have a point P initially, x1, y1, z1 in earlier coordinate system, and by shifting the origin, this is our new rectangular coordinate system. We want to find the coordinates of this point P in our new coordinate system. So we want to say this P, the coordinates of P are x1 dash, y1 dash, and z1 dash. So what is the relation between x1 dash and y1 dash? So x1 dash and x1. So this is this. x1 dash is x1 minus x dash. y1 dash is y1 minus y dash, and similarly z1 dash is z1 minus z dash. So this is the relation. So by shifting the origin, by moving the axes parallel to themselves, this is the relation which we get between the new coordinates and the earlier coordinates of a particular point. So having read about all this, let's take a few examples. Say we have our origin 0, 0, 0 shifted to 1, 2, minus 3. We have to find the coordinates, the new coordinates find new coordinates of the point 0, 4, 5. I'll once again repeat the question. That our origin is shifted to 1, 2, minus 3. We have to find the new coordinates of the point 0, 4, 5. So as we have studied just now, we have P, x1, y1, z1 as 0, 4, 5. We have to find P dash, x1 dash, y1 dash, z1 dash. Given origin is shifted to 1, 2, minus 3. So say x dash is 1, y dash is 2, z dash is minus 3. So x1 dash is x1 minus x dash is equals to 0 minus 1 equals to minus 1. Similarly y1 dash is y1 minus y dash is equal to 4 minus 2 is equals to 2. Similarly z1 dash is z1 minus z dash is equals to 5 minus 3 is 8. So P dash is equals to minus 1, 2 and 8. So in this way we can find the new coordinates of the system under the translation of axis. Let's take one more example. We have to show that these 3 points, point A, which is given by 3, minus 2, 4, B, which is given by 1, 1, 1, and C, minus 1, 4, minus 2. We have to show that these 3 points are collinear. Show. Okay. So there are many ways to show this. I'll use section formula to show that these 3 points are collinear. So say we have 2 points A and C. If B lies on the line joining A and C, that is A, B and C are collinear, then B will divide the line A and C in say some ratio, that is lambda is to 1. So the coordinates of B will be xb will be lambda xc plus xa upon lambda plus 1, which will be equal to minus lambda plus xa upon lambda plus 1. Similarly, yb will be lambda yc 4 lambda plus x plus ya minus 2 upon lambda plus 1. Similarly, zb will be lambda yc plus 4 upon lambda plus 1. So if we can find a particular value of lambda such that 1 comma 1 comma 1 satisfies all these 3 points, we can show that B lies on the line joining A and C. So suppose we put the value of lambda equals to 1. Put lambda equals to 1. So what we get, xb as 1, we get yb as 1, we get zb as 1. So by putting lambda equals to 1, we get the same points of B as are here. So B divides A and C in the ratio 1:1. That is, B is the midpoint of the line joining A and C. So these 3 points are collinear. This is a very useful property to show the collinearity of 3 points. Okay. Okay, so let's now start with something new, say direction. Direction ratios and direction cosines. First of all, I'll start with direction cosines. I'll use short forms. I'll use DC to represent direction cosines and DR to represent direction ratios. Okay, so say a particular line forms angle alpha, beta, gamma with the positive x, y and z axis respectively. So this is our rectangular coordinate system. This is y axis, this is x axis, this is z axis. We have a particular line, say this, it forms angle alpha with the x axis, angle beta with the y axis and angle gamma with the z axis. So the direction cosines of this line are cos alpha, cos beta and cos gamma. So I once again repeat that if a particular line makes angle alpha, beta and gamma with the positive direction of x, y and z axis respectively, then the direction cosines of that line are cos alpha, cos beta and cos gamma. We usually represent direction cosines by L M N, where L represents cos alpha, M is cos beta and N is cos gamma. So direction cosines basically represent the direction of a particular line, and cos square alpha plus cos square beta plus cos square gamma is 1, which is very important and it should be noted. That this is very important property of direction cosines, that cos square alpha plus cos square beta plus cos square gamma is 1. Okay. So this is about direction cosines. Direction ratios are similar to direction cosines. They also represent a direction of a line. The difference being that the direction squares of the sum of the squares of the direction cosines is equal to 1, while for direction ratios it is not the same. Direction ratios are just proportional to direction cosines. So the direction ratios, say DRs are A, B, C. So then these will be proportional to LMN, that is A by L will be equal to B by M will be equals to C by N. So this is about direction ratios. If we are given direction ratios of a particular line, we can easily find direction cosines by using the property that L square plus M square plus n square is equals to 1. So if we solve these two equations, we easily get that L is a upon summation a square, m is b upon summation a square, and n is c upon summation a square. So this is about direction cosines and direction ratios. So basically, I once again repeat that the main use or the most important properties of direction cosines and direction ratios are that they represent the direction of a particular line. Also, say we have a point x, y, z 0, 0, 0. We have a point P, say x, y, z. Then this line OP can also be written as say this is R. So if we usually write OP as R cos alpha I cap plus R cos beta j cap plus R cos gamma k cap, that is RL I cap plus RM j cap plus Rn k cap, where Lmn are direction cosines of this line, that is the line joining origin and the point P. Okay, so this is about direction cosines. This is alpha, this is beta, and this is gamma. Okay, so let's now take a few illustrations. Okay, just before taking illustrations, I would like to mention the use of direction cosines. Direction cosines represent the direction of a particular line. They are used to find the angle between two lines. Okay, so say we have two lines. Say we have two lines, the direction cosines of which are L1, that is line 1, L1, M1 and N1. Line 2 has direction cosines L2, M2 and N2. So the unit vector along the direction of first line is L1 I cap plus N1 M1 j cap plus N1 k cap. Similarly, second line is L2 I cap plus M2 j cap plus N2 k cap. So the angle between both the lines is, that is, we have to take the dot product of these vectors. Say this is V1, this is V2. So V1 dot V2 is V1 V2 cos theta. Theta is the angle between both the lines. So this is L1 L2 plus M1 M2 plus N1 N2 is 1 cos theta. So the angle between both of the lines is L1 L2 plus M1 M2 plus N1 N2. So this is very important. If we have the direction cosines, if we have the direction ratios also, we can easily convert from direction ratios to direction cosines. And if we have direction cosines, then the angle between two lines can be easily represented in terms of direction cosines. So if we have the angle, we can also check for parallel or perpendicular lines. So say L1, so now L1, case 1 is L1 is parallel to L2. So theta should be 0. So both the lines should be parallel. So the condition is that L1 by L2 should be equals to M1 by M2 should be equal to N1 by N2. This is the condition for both lines to be parallel. Second is L1 is perpendicular to L2. So the condition is, if it is perpendicular, then cos theta is 0. So now L1 L2 plus M1 M2 plus N1 N2 is 0. So these are the conditions for lines to be parallel or perpendicular. So this is about direction cosines. Let's take a few examples. Direction ratios are given as 2, minus 3, 6. We have to find the direction cosines. So it is very easy. We have already learned this. Say direction cosines are Lmn. So L was 2 upon 2 square plus minus 3 square plus 6 square under root, which is 2 upon 4 plus 9 plus 36, which is 9 and 4 13, 36 and 9 7, that is 2 upon 7. Similarly, m is minus 3 upon 7 and n is 6 upon 7. We can easily see that L square plus m square plus n square is equals to 1, which is very important property and which differentiates direction cosines and direction ratios. Another question is that if alpha, beta, gamma are respectively the angles which a particular line makes with x with the positive direction of x, y and z axis, show that sine square alpha plus sine square beta plus sine square gamma is 2. This is also quite easy. We already learned that cos alpha, cos beta and cos gamma are the direction cosines of the line, and sum of the squares of direction cosines is equals to 1. So cos square alpha plus cos square beta plus cos square gamma is 1. So cos square alpha is 1 minus sine square alpha. Similarly, cos square beta is 1 minus sine square beta. Similarly, cos square gamma is 1 minus sine square gamma is equals to 1. So sine square alpha plus sine square beta plus sine square gamma is equals to 2. This was an easy question. Okay. Let's take one more question. Okay, before taking another question, I'd like to mention one important property, that we want to find projection of a particular line on another line. Say we have a line and another line. The direction cosines of this line are Lmn, and say this is a line from A, x1, y1 and z1 to B, x2, y2 and z2. So we want to find the projection of the line AB along this line. So the projection, I denote this projection by say some particular say projection P is equal to L x2 minus x1 plus m y2 minus y1 plus n z2 minus z1. This is the projection of the line AB on this particular line. Okay. Also say we have to find the perpendicular distance from a particular point on a given line. Say this is a particular line with direction cosines Lmn. This is a particular point, say P, with coordinates x, y, z, say, and we want to find the perpendicular distance from P to this line. We will be given a particular point, say A, x1, y1 and z1 on this line. I once again repeat, there is a particular line passing through A, x1, y1, z1 and which has direction cosines L, M and N, and we have a point P, x, y, z. We want to find the perpendicular distance from P to this line. So the process is that join A and P. We know this distance by the section formula, by the distance formula, sorry, and we now learn how to find the projection of a particular line on another given line. So we have to find the projection of this line on this line, and then we can find this perpendicular distance by using the Pythagoras theorem. I'll show an example to depict this. Say this point P is given as 0, minus 1, 3, and I'll reframe the question. the question is that we have a point P 0, comma, minus 1, comma 3. I have to find the perpendicular distance from P to the line joining point A, which is given as 1, comma, minus 3, comma 2, and B, which is given as 2, comma, minus 1, comma 4. So I have to find the perpendicular distance from this point to the line joining A and B. So this is point P, this is the line joining A and B. Suppose I have to find this distance. So this is point A, so I have to find the direction cosines of this line. So since 2 points on this line are given, so I can find the direction ratios easily. So direction ratios are x2 minus x1 is equals to 2 minus 1 equals to 1, y2 minus y1 is equals to minus 1 minus minus 3 is equals to 2, z2 minus z1 is 4 minus 2 is equals to 2. So the direction ratios are L is equals to 1 upon 1 square plus 2 square plus 2 square. So this is 4 plus 4 plus 8 is 1 by 3. Similarly, M is 2 by 3 and N is also 2 by 3. So the direction we know, so now we know the direction cosines of the line. So we can find the projection of this line AP on this line. So this is Q. So the projection AQ is given by the formula L into the difference of the coordinates of P and point A, that is L 0 minus 1 plus M minus 1 minus minus 3, which is plus 3, plus N 3 minus 2. So this is minus L, L is 1 by 3 plus M is 2 by 3 into 2 plus N is also 2 by 3 into 1. So AP is 4 by 3 plus 2 by 3, 6 by 3, 2 minus 1 by 3, 2 minus 1 by 3, that is 5 by 3. So this is AQ. So now we have to find AP. AP can easily be found using section formula, that is 0 minus 1 whole square, 1 square, minus 1 minus minus 3, that is 2 square, plus 3 minus 2, that is 1 square again. So this is 4 plus 1 6 under root 6. So this is AP. So we have AQ, we have AP. Now PQ square plus AQ square is AP square. This is using Pythagoras theorem. So PQ square is what we have to find. AQ square we know. AQ square is 25 by 9 and AP square is 6. So now we can easily find PQ. So I once again repeat the entire procedure. We want to find the perpendicular distance from the point P to a particular line, and 2 points on the line are given. So what we do first is, with the help of both of the points A and B, we find the direction cosines of the line. Then with the help direction ratios of the line, then with the help of those direction ratios, we find the direction cosines of the line. And once we have the direction cosines of the line, we use our formula which we studied just now to find the projection of the line AP on the line AB. Say this is point B somewhere. And then we have AQ. We know AP by distance ratio. Then using Pythagoras theorem in the triangle APQ, we can easily find PQ, which is the perpendicular distance from the point P on the line AB. Okay. So this was about direction ratios and direction cosines. So now let's move on to another topic. Before going to another topic, I would like to mention one important property, that area of a triangle. Say we have a triangle ABC. Coordinates are x1, y1, z1 as we usually take. So now the area of the triangle is defined in this way. We define delta x, which is half x1, y1, 1, x2, y2, 1, x3, y3, 1, delta y, which is half y1, z1, 1, y2, z2, 1, y3, z3, 1. Similarly, delta z, half the determinant of z1, x1, 1, z2, x2, 1, z3, x3, 1. So we find these three determinants, and then the area of the triangle delta is delta square is defined as delta x square plus delta y square plus delta. So I once again repeat that we have a triangle ABC, the coordinates of which are x1, y1, z1, x2, y2, z2 and x3, y3, z3 respectively. Then the area of the triangle represented by delta is defined in this way. We find delta x, which is half the determinant x1, y1, z1, x2, y2, z2 and x3, y3, z3. Similarly, delta y and delta z. Then delta square is sum of the squares of delta x, delta y, delta z. We can take a very simple example. Say we have 3 points. Say this is 4, 4, 4. Say this is 6, 0, 0. This is say 0, 0, 0. We want to find the area of this triangle. So we can just replace x1. Say this is x1, x2, x3. So x1, y1. This is x1. This is y1, z1, x2, y2, z2, x3, y3, z3. So x1, y1 is 4, 1, x2, y2, x3, y3. So the area is half four 0 minus 4 0 minus 6 plus 1 0. So this is half into 4 6 at 24. So this is 12. Similarly, let's replace here y1 and z1, y2 and z2, y3 and z3. That is 4 4. Y2 and Z2 is 0, 0. Y3 and Z3 is also 0 and 0. So this is 0. 4, 0, 4, 0, 0. Similarly, let's find this Z1, Z2, Z3, x1, x2, x3. So this is 4, 0, 0, and that is 4, 0, 6. So this is half 4 minus 6 is equals to minus 12. So this is delta x, delta y, delta z. So delta is defined as delta square is delta x square plus delta y square plus delta z square, which is 144 plus 0 plus 144. So therefore delta is 288 under root, which is 12 root 2. So 12 root 2 is the, in square units, is the area of this triangle. Okay. So once covered this basic stuff, let's move on to more intricacies of three-dimensional geometry. Okay, So now let's talk about plane. Plane is a three-dimensional entity. Plane is basically the locus. Every three-dimensional figure is locus of a point. So what is a plane? Plane is a locus of a point P such that if there is any other point on the locus Q, and if we join P by Q, if we join P and Q, then any point on the line joining P and Q should also lie on the plane. I once again repeat that plane is a locus of a point P such that if there is another point Q on the locus of P, and if we join P and Q, then the line joining P and Q has all the points on the locus of P. So that is a plane. In this way we define a plane. So first of all, let's move on to the representations of a plane in our coordinate geometry. So there are various ways to represent a plane. So some of the most standard ways are this is a plane with A, B and C at the direction ratios of the normal to the plane. This is also a plane with L, M, N as the direction cosines of the normal to the plane. Important property of this representation is that P is the perpendicular distance from the origin to the plane. Say we have a point x1, y1, z1 lying on the plane. So the equation for the plane is A x minus x1 plus B y minus y1 plus C z minus z1 is equals to 0. So this is the equation of the plane when we have a point on the plane given to us. A, B and C are the direction ratios of the normal to the plane. If we have say 3 points x1, y1, z1, x2, y2, z2 and x3, y3, z3 on the plane, or in other words we have 3 points x1, y1, z1, x2, y2, z2 and x3, y3, z3. We want to find a plane passing through these points. So the equation can be found by solving this determinant. By solving this determinant, we can find the equation of the plane. This reminds us of the scalar triple product. We can see that these are basically the 3 lines. So these 3 lines are coplanar. So the box product of these 3 lines is equal to 0, and this is what exactly is written here. So this is the way to find the equation of the plane when we have 3 points. There is also one important property to find the equation of the plane when we have been given the axis intercepts. Say the equation is then x by A plus y by B plus z by C is equal to 1. So this is the equation of the plane when A, B and C are the positive axis intercept of the plane. That is, this plane intersects the positive x-axis, and the coordinate of the point of intersection of this plane with the positive x-axis is A, 0, 0, with positive y-axis is 0, B, C, with z-axis is 0, 0, C. So these are the basic 5 representations of a plane. The question is, find the plane passing through (2, -1, 3), which is the foot of perpendicular from the origin on the plane. I once again repeat the question that we have to find the plane which is passing through this point, and this point is the foot of the perpendicular from the origin on the plane. So using our representation to find the equation of the plane when a point is given, it was a x minus x1 plus b y minus y1 plus c z minus z1 is equals to 0. So this is the equation of our plane. Now we know that if we join origin with this point, this line is perpendicular to the plane. So this line is actually normal to the plane. So the direction ratios can easily be found by this. So we can take, so the direction, so if this is the plane, this is our origin, this is this point 2, minus 1, 3. So direction ratios are direction ratios can be found directly as 2 minus 0 equals to 2, minus 1 minus 0 equals to minus 1, 3 minus 0 equals to 3. So this is equals to A, this is equals to B, this is equals to C. So plane, the equation of the plane is twice of x minus 2 minus 1 y plus 1 plus 3 z minus 3 is equals to 0. So this is the equation of the plane which is passing through this point, and this point is the foot of the perpendicular from the origin on the plane. Okay. Now angle between two planes. We have two planes, we want to find the angle between them. So see, the first plane is given as a1x plus b1y plus c1z plus d1 equals to 0, and second plane is a2x plus b2y plus c2z plus d2 is equals to 0. So we want to find the angle between these two planes. Angle between the planes is actually the angle between the normals to the plane. So we know that the normal to the first plane has direction ratios a1, b1 and c1. Similarly, normal to the second plane has direction ratios a2, b2, c2. So the angle between both the planes is a1 square plus b1 square plus c1 square under root dot a2 square plus b2 square plus c2 square under root cos theta is a1 a2 plus b1 b2 plus c1 c2. This is basically the scalar product. So in this way we can find cos theta, that is the angle between both of the planes. So P1 is case 1, P1 is parallel to P2. So this is when A1 by A2, both the normals are parallel, is C1 by C2. Similarly, case 2, P1 is perpendicular to P2. So this is when this is 0, cos theta is 0. So A1 A2 plus B1 B2 plus C1 C2 is 0. So this is the condition for two planes to be parallel and perpendicular. Let's now study about position of a point with respect to a plane. So say we have a point P and we want to find that on which side the point P lies on the plane. So basically position of a point is dealt with respect to 2 points. We have 2 points, say P and Q, and we have a plane. So we want to find whether points P and Q lie on the same side of the plane or on the opposite sides of the plane. So say the plane is, usually we represent plane by the letter pi. Say A1x plus B1y plus C1z is 0, and say point P is x1, y1 z1, point Q is x2 y2 z2. So point case 1, P and Q are on same side of plane if a1 x1 plus b1 y1 plus c1 z1 and a1 x2 plus b1 y2 plus c1 z2 are of same sign. So P and Q are on the same side of the plane if a1 x1 plus b1 y1 plus c1 z1 and a1 x2 plus b1 y2 plus c1 z2 are of same sign. Similarly, opposite side, if a1 x1 plus b1 y1 plus c1 z1 and a1 x2 plus b1 y2 plus c1 z2 are of different sign. So this is the way to find the position of a point with respect to a plane. And the topic is perpendicular distance of a point to a plane. So we have to find the perpendicular distance from a point to a plane. So this is the plane ax plus by plus cz plus d equals to 0. This is point P, x1, y1, z1. We have to find the perpendicular distance. So this distance d is given as ax1 plus by1 plus cz1 plus d upon a square plus b square plus c square under root whole modulus. So this is the perpendicular distance from the point P to the plane. There is also a notion of the distance between two parallel planes. Say plane first is and plane second is. The planes are parallel, so the normals have same direction ratios. So the way to find the perpendicular distance between them is that first convert these direction ratios into the direction cosines. So we can rewrite plane 1 as a upon a square plus b square plus c square under root x. Similarly, b upon a square plus b square plus c square y plus c upon a square plus b square plus c square z is d1. Similarly, we can write p2 as a square plus b square plus c square a upon summation a square under root x plus b upon summation a square under root y plus c upon summation a square under root z is d2 upon summation a square under root. So we already showed that this is the perpendicular distance from the origin to this plane. Similarly, this is the perpendicular distance from the origin. So it is like this. This is plane 1, this is plane 2 parallel to this. This is origin. So this is d1 and this is d2. So the distance d is d2 minus d1, which is d2 upon summation a square minus, so this is d1 dash d2 dash d dash d2 dash. So this is the distance between two parallel planes. Fine. Another notion is family of planes. Say we have a plane u equals to 0 and a plane v equals to 0, then the equation of the plane which is passing through the line of intersection of these two planes can be given as u plus lambda v is equal to 0. This is the general form of the equation of the plane which is passing through the line of intersection of the planes u and v. So let's take a specific example. So the question is, we have two planes ax plus by plus cz plus d is equals to 0 and alpha x plus beta y plus gamma z plus delta is equals to 0, and so we have these two planes. We have to find the plane passing through the line of intersection of these planes and perpendicular to xy plane. So the solution is through family of planes. So we know that the plane which is passing through the line of intersection of these planes can be written as ax plus by plus cz plus d plus some lambda times alpha x plus beta y plus gamma z plus delta is equals to 0. Now this plane is perpendicular to xy plane. We know that xy, the equation of xy plane is z is equals to 0. So this is a plane, this is a plane, these two are perpendicular. So the normal of these two planes are perpendicular. So the normal to this plane is, this plane can be rewritten as x a plus lambda alpha plus y b plus lambda beta plus z c plus lambda gamma plus d plus lambda delta is equals to 0, and this is z is equals to 0. So these two planes are perpendicular, so the normals are perpendicular. So using the condition for perpendicularity of two planes, we get lambda is minus c by gamma. Putting lambda here, we can find the equation of the plane. There is also one important property. Say we have two planes, pi 1 is a1x plus b1y plus c1z plus d1 is 0, and pi 2 is a2x plus b2y plus c2z plus d2 is 0. Now we have to find the bisector plane of these two planes. So the bisector planes are given as a1x plus b1y plus c1z plus d1 upon summation a1 square is equals to plus minus a2x plus b2y plus c2z plus d2 upon summation a2 square. I once again repeat that these are the equations of the bisector planes of these two planes. That is a1x plus b1y plus c1z plus d1 upon divided by the square root of the sum of squares of the direction ratios of the normal is equal to plus minus a2x plus b2y plus c2z plus d2 divided by square root of a2 square plus b2 square plus c2 square. Okay. So one very important property is that we get here two bisector planes. Now one plane bisects the acute angle between the planes and the other plane bisects the obtuse angle. So how do we find that which plane bisects the acute and which plane bisects the obtuse? So the way is that suppose you get one equation keeping the positive sign, then find the angle this plane makes with any other plane. If that angle is less than 45 degree, so that plane bisects the acute angle. If the angle is greater than 45 degrees, so that plane bisects the obtuse angle. So let's take an example. So we have two planes. Plane 1 is given as x plus 2y plus 2z is equals to 9. Plane 2 is given as 4x minus 3y plus 12z plus 13 is equals to 0. So these are two planes. We have to find the bisector planes of these planes and tell which bisector plane is acute angle bisector and which is obtuse. Solution is this. So first let's write both of the bisectors. So this is the final equation of the two planes. Okay, so now let's take both the cases. Say case 1, keeping the positive sign. So if there is positive sign, the equation is 13x plus 26y plus 26z minus 117 is equals to 12x minus 9y plus 36z plus 39. So x plus 26 plus 9 is 35 minus 10z is equals to 156. Okay. Fine. Now the second is keeping the negative sign. (26 and 36). Okay, so this is the equation keeping the positive sign, this is the equation keeping the negative sign. So here we get two planes. Now we have to find which plane is the acute angle bisector, which is the obtuse angle bisector. So let's take this plane, x plus 35 y minus 10z is 156. And let's take this pi1 plane, x plus 2y plus 2z is equals to 9. Let's find the angle between both of them. So that is 1 square plus 35 square plus 10 square. 1 square plus 2 square plus 2 square cos theta is 1 plus 35 into 2 is 70 minus 40. So this is 101 plus 35 square, and this is 3 cos theta is 70 is this 31. So cos theta is 31 divided by 3, 35 square. Let's find 35 square. That is 1225 plus 101 6231. Okay, so this is the cos theta. So we have to find whether theta is less than 45 degree or not. So we know that cos 45 degree is 1 by root 2, and below 45 degree cosine is greater. So if we can show that this angle is this value is greater than 1 by root 2, this is less than 45 degree, and if this value is less than 1 by root 2, that is greater than 45 degree. So this is greater than 1 by root 2. Yeah, this is almost greater than 1 by root 2, since 31 into 31 is 961. 31 into 31 is 961, and below it is written as 9 6 are 54, 5 9 2 are 18, and 5 is 23, 2 9 3 27, 29, 2 9 1 are 9 and 2 11, and 961 twice is the twice of 961 is, I'm sorry, so clearly this is less than 1 by root 2. So theta is greater than 45 degree. So this plane is actually the obtuse angle bisector, and this is the acute angle bisector. So this is the way to find whether the plane is an acute angle bisector or obtuse angle bisector. Fine. So now let's move on to a different topic altogether. We have almost covered about planes. Now let's study about lines. What is a line? We usually deal with straight line. So there are many representations of a straight line. We will mostly deal with two basic representations. First is that line is mostly represented by the intersection of two planes. So we will be given a plane a1x plus b1y plus c1z plus d1 is equals to 0 equal to some other plane. So this is the equation of a line, And what we mean by this representation is that this line is the line of intersection of these two planes. Another representation of the line is the parametrical form. So this says that this is a line which is passing through the point x1, y1, z1, and the direction ratios of the line are a, b, and c. These two forms are interchangeable. So this is the basic structure. So let's take a few examples. That the example says that we have to find the coordinates, of the foot of perpendicular from the origin to the plane to the plane 3x plus 4y minus 6z plus 1 is equal to 0. So we have to find the coordinates of the foot of perpendicular from the origin to this plane. Okay, so how do we proceed? Okay, so let's find the line joining the origin and the foot of the perpendicular to this plane. So we know that this line has one point as origin. So using the form as x minus x, using the parametrical form, we know that this line passes through origin. So x1, y1, z1 can be termed as 0. So this can be x by a is equals to y by b is equals to z by c is equals to 0. Also, this line is perpendicular to the plane. Since this line is from the origin to the foot of the perpendicular to the plane, so the direction ratios are actually along the normal to this plane. So a is 3, b is 4, and c is minus 6. So the equation becomes x by 3 is equals to y by 4 is equals to z by minus 6 is equals to, say, this is not 0, I'm sorry, this is a particular lambda, say lambda. So x is 3 lambda, y is 4 lambda, and z is minus 6 lambda. So any point on this line has the coordinates which are parametrically represented by this. Now to find the foot of the perpendicular, that particular point lies on this plane. So satisfying these three coordinates in the equation of the plane, (3x plus 4y minus 6z plus 1 is equals to 0. So x 3 lambda, y is 4 lambda minus 6, z is minus 6 lambda plus 1 is 0. So 9 lambda plus 16 lambda plus 36 lambda is equals to minus 1. So this is 25. 25 and 36 is, this is 25 and 36 is 41, 51, 61. Lambda is minus 1. So lambda is minus 1 upon 61. So putting the value of lambda here, we get the coordinates of the foot of the perpendicular. Okay, so now let's move to line and plane together. So the basic problem in this scenario is finding the angle between a line and a plane. So say the angle between line and normal to the plane is theta, then angle between line and plane is y by 2 minus theta. That is, say the line is x minus x1 by a is y minus y1 by b is z minus z1 by c, and the plane is, say, a1x plus b1y plus c1z is d1, then the angle between the line and the normal to the plane will be theta is the angle between the line and the normal to the plane. So the actual angle theta, angle between line and normal to the plane. So the actual angle phi is pi by 2 minus theta, where phi is angle between line and plane. So this is very important, that angle between two planes is the angle between the normals of the plane, but angle between a line and a plane is 90, is the angle the line makes with the plane is defined in this way, that first of all we find the angle between the line and the plane, say that the angle is line and the normal to the plane, say that angle is theta, so then the angle between the line and a plane is pi by 2 minus theta. Fine. So this was about angle between line and a plane. Another issue is equation of a plane passing through a line. We have to find the equation of a plane which is passing through a particular line. So say the line is given in two possible interpretations. First of all, say it is given as the intersection of two planes. Say the line is given in this representation, then the plane which is passing through the line of intersection of these planes is, using the family of lines, so u plus lambda v is equals to 0. So this is the plane which is passing through the line of intersection of these planes. If the line is given in this format, that is x minus x1 by a is y minus y1 by b is z minus z1 by c is 0, is lambda. So how do we find the plane which is passing through this line? So we know that x1, y1, z1 is on this line. So a plane which is passing through x1, y1, z1 can be written as this is the general equation of a plane which is passing through x1, y1, z1. Now we know that this plane contains this line. So the normal to this plane, which has direction ratios as a1, b1, c1, is perpendicular to this line which has direction ratios a, b and c. So a1a plus b1b plus c1c is 0. So these are the two ways to find the equation of a plane which is passing through a line. Let's take an example to clarify this point. Find the equation of the plane containing the parallel lines x plus 1 by 3 equal to y minus 2 by 2 equals to z by 1 and x minus 3 by 3 equals to y plus 4 by 2 is equals to z minus 1 by 1. So we have to find the equation of the plane which is containing both these parallel lines. So we will use the above mentioned analogy that since the plane passes through these two lines, so the plane contains these 2 points. That is, first point is minus 1 comma 2 comma 0 and second point is 3 comma minus 4 comma 1. So the points are minus 1 comma 2 comma 0 and 3 comma minus 4 comma 1. So plane contains these 2 points. So equation of the plane can be written as a x minus x1 plus b y minus y1 plus c z minus z1 is equals to 0. Okay, so now we know that this plane contains point B as well. So satisfying point B here gives a x is 3, 3 plus 1 is 4 plus b y is minus 4 minus 4 minus 2 is minus 6, c z is 1 is 0. So this is one equation we get, that is 4a minus 6b plus c is 0. That is the first equation. Now how do we get the second equation is, since the plane contains this line, so normal to the plane is perpendicular to this vector 3 I cap plus 2 j cap plus 1 k cap. So 4 square plus a square plus b square plus c square 3 square plus 2 square plus 1 square. Since they are perpendicular, we can directly use AL plus BM, 3A plus 2B plus 1C is equals to 0. This is the second equation. So using the value of C from here, we get 3A plus 2B, C is 6B minus 4A. C is 6B minus 4A is equals to 0. So this is 8B minus A is equals to 0. So A is equals to 8B. Now putting A here in terms of, putting B here in terms of A, we get 4A minus 6. B is A by 8 plus C is 0. So we get, or it's better if you put A in terms of B. A is 8B minus 6B plus C is 0. Therefore C is 8 4s are 32 minus 6 is 26. C is minus 26B, A is 8B. So we can write this equation as A x plus 1 plus b y minus 2 plus cz is equals to 0. A is 8b x plus 1 plus b y minus 2, c is minus 26bz is 0. So 8x plus 8 plus y minus 2 minus 26z is 0. So this is the equation of the plane which is parallel, which contains both of these lines. Fine. Okay, now let's take some minimal issues. First, foot of the perpendicular from a particular point, say P, to plane pi. So we have to find the foot of the perpendicular from a point P to a plane pi. So the way to find this is that find a line starting from P and along the normal to the plane. Now since you have the equation of the line and equation of the plane, solve them to get the foot of the perpendicular. Second is image of P in plane pi. So this is just a consecutive approach to this problem. Since you find the feet of the perpendicular from the point P to the plane pi, so the image is, say this is the plane pi, this is point P, you find, we have already found Q in the first part. I once again repeat the way to find Q. From P, find the equation of the line which is passing through P and which is along the normal to the plane. You have the equation of the line, you have the equation of the plane, solve them to get the point Q. Once you have point Q, point P dash, which is the reflection of point P in the plane pi, it can easily be found as, say this has coordinates x1, y1, z1, this has coordinates x1 dash, y1 dash, z1 dash, and you get coordinate of Q as x, y, z. So x is x1 plus x1 dash upon 2. Similarly, so since you know, you have already found x, you know x1, so using both of them you can find x1 dash, similarly y1 dash and z1 dash. So this is the way you find image of a point P. Now you have to find we have to find the image of a line and projection of a line. Projection of a line on a plane. Okay, so we have to find the projection of a line on a plane. Say this is our plane and this is our line. So to find the projection of this line on this plane, what we do is we find the intersection of this line with this plane. Say this is A. We find the foot of the perpendicular, this is the point P. We find the foot of the perpendicular. Using this, we can find the foot of the perpendicular from a point P to the plane. So this is, say, B. Now we want to find AB. We know AP, we know PB, we can find AB. Similarly, if you want to find the image of a line on a plane, what we can do is, the image is simply like this. So the way to do is, find A using the intersection of the line and the plane, find P dash, which is the image of P, and so AP dash is the image of the line in the plane P. So we can find P dash from this image of a point in plane pi, and then we can find image of a line in a plane. So this is very easy. I once again just summarize that we can find the image of a point in a plane. We can find the foot of the perpendicular from a point in the plane. The way to find is draw the line or make a line from the point P, which is along normal to the plane. Now the intersection of that line with the plane gives the foot of the perpendicular. Now to find the image of a point, since we have the foot of the perpendicular, we have the point, we can use the midpoint formula to find the image of the point. Once we have the foot of the perpendicular and the image of a particular point with respect to a particular plane, we can also use these concepts to find the projection of a line and the image of a line according to a particular plane. Say we have two lines, L1 and L2. We want to find a line which is intersecting both of them. So say L1 is given as A1x, L1 is given as x minus x1 upon A1 is equals to y minus y1 upon b1 equals to z minus z1 upon c1, that is L1, and L2 is given as x minus x2 upon A2 is equals to y minus y2 upon b2 is z minus z2 upon c2. So this is L1 and this is L2. So we want to find a line which is intersecting both of them. So how do we find it? Say this is some R1 and this is say some R2. So we know in terms of R1 the coordinates of any point which is on line L1. Similarly in terms of R2 we know the coordinates of any point which is on the line L2. So the line which is intersecting both L1 and L2, that line should pass through some point of L1 and some point of L2. Say for a particular R1 we have point P which has the coordinates x equals to A1 R1 plus x1, y is equals to B1 R1 plus y1, and z is equals to C1 R1 plus z1. Similarly for a particular point Q on line L2, x is equals to A2 R2 plus x2, y is B2 R2 plus y2, and z is C2 R2 plus z2. So we have points P and point Q. So now our line is the line joining P and Q. And given some special constraints, we can eliminate R1 and R2. Okay. And actually, yeah, we can find R1 and R2 since, fine. So now let's move on to another topic, which is shortest distance between two lines. We have two lines, two skew lines. Skew lines are those which are not parallel and also they are not intersecting. In 3-dimensional it is possible, in 2-dimensional it is not possible. So we have to find the shortest distance between two lines. So the way to find is, we know the equation of both of them. So the shortest distance PQ is along the line which is perpendicular to both of them. I once again repeat, so we have to find, this is the shortest distance and the line PQ is such that it is perpendicular to both of them. So I'll take an example to show how to find the distance between two skew lines. Say we have a line L1 which is x minus 3 by 3. And a line L2 which is x plus 3 by say R1, say R2. So I have to find the shortest distance between them. So how do we go on? So first of all, any point on this line can be written as, say some point P can be written as x is 3 R1 plus 3, y is minus R1 plus 8, and z is R1 plus 3. and any point on this line can be written as x is minus 3 r2 minus 3, y is 2 r2 minus 7, and z is 4 r2 plus 6. So these are the 2 points. So say this is L1, this is L2, this is PQ, perpendicular, perpendicular. So this line PQ is perpendicular to L1. So the direction ratios of the line PQ are ratios of PQ are this minus this minus this, and this minus this. So minus 3r2 minus 3r1 minus 3 minus 3 minus 6 comma 2r2 plus r1 minus 7 minus 8 is minus 15 comma 4r2 minus r1 plus 3. 6 minus 3 is 3. Yeah, okay. So these are the direction cosines of PQ. So this is perpendicular to the line L1 as well as to the line L2. So using the condition of perpendicularity of two lines, we get first equation as minus 3r2 minus 3r1 minus 6 into 3 plus 2r2 plus r1 minus 15 into minus 1 plus 4r2 minus r1 plus 3 into 1 is 0. So that is r2, that is minus 9, that is minus 2, that is 4, r1, that is minus 9, that is minus 1, that is minus 1, then minus 18 plus 15 plus 3 is 0. So this is r2, minus 11 plus 4 is minus 7, plus r1, that is minus 11 is 0. So this gives 7 r2 plus 11 r1 is 0. This is the first equation. This is also perpendicular to L2. So minus 3 r2 minus 3 r1 minus 6 into minus 3 plus 2 r2 plus r1 minus 15 into 2 plus 4 r2 minus r1 plus 3 into 4 is also 0. So r2 minus 9, plus 9 plus 4 plus 16 plus r1 9 plus 2 minus 4, then plus 18 minus 30 plus 12 is 0. So this gives 16 and 4 20, 29 r2 plus 7 r1 is 0. So we have these two equations, and these two equations satisfy r1 is equals to r2 equals to 0. That is, if we solve both of them, if we solve this equation and this equation, the only values of r1 and r2 we satisfy both of them is r1 equals to r2 equals to 0. So the points P and Q are finally are putting r1 equals to 0, x is 3, y is 8, Z is 3. Similarly, Q is X is minus 3, Y is minus 7, Z is 6. So the distance between the lines is similarly PQ is equals to 3 plus 3 whole square plus 8 plus 7 whole square plus 3 minus 6 whole square under root. So this is 36 plus 15 square is 225 plus 3 square is 9. So this is 45 and 225 is 270 under root. So this is the final distance between the skew lines. So here I think I was able to cover the relevant topics pertaining to 3D, and as far as I know, as far as the syllabus of the entrance examinations of engineering as well as the 12th board examination, this is the required syllabus, and you can get back to us if you have any queries relating to 3D. Thank you.